Hey there, and welcome back to Abstract Algebra. In this third of what will be 4 video lectures in the material in section 4.5, we're going to continue to draw the strong analogy between the ring of integers and the ring of polynomials over a field. And in particular, today I want to tell you about greatest common divisors in the polynomial ring. All right. So you can see the goals there. Let me just kind of walk you through them. I want to define what I mean by division or divisibility in the polynomial ring. I want to define what I mean by the greatest common divisor of 2 elements in the polynomial ring, what I mean by relatively prime polynomials, and then I want to prove a version of Euclid's lemma. It's theorem 4.510 in your book. You know, I think it might be a good idea if you want to pause this lecture right now and go back into the section, I'm looking it up right now, it's section 5 in chapter 1. It's called the integers, and maybe reread that section, because in that section we define divisibility in the integers. The greatest common divisor of integers is defined, relatively prime integers is defined, and then that Euclid's lemma is proved there for the integers. I'm trying to look for it as I'm speaking to you right now. Euclid's lemma, it's theorem 1.55. Let me write that here as we're going. So I personally think maybe before we get going in all of this business about polynomials, you might want to go back and check out section 5 in chapter 1. Remind yourself of these notions in the integers, because what I'm going to be doing is kind of drawing analogies between those notions and how things work here in this polynomial ring. Okay? So let's just get going. I've written out the proofs here, so I'm just going to narrate them. Probably be talking fast and going through this stuff at a pretty quick pace, but you can stop the video and think about what I'm doing. Maybe think about some examples, grab a couple of particular polynomials and multiply them, try to work this out as we go so it becomes more concrete. Okay, so here's the first definition. We're going to, given 2 polynomials, f and g, one of them not 0, the one I'm going to be dividing by. I'll use my usual convention. If I've highlighted something in blue, it's a vocab term. Make a flashcard for it. Know this definition. Be able to state this definition by rote memory. So I'm going to say that g divides f. And we'll write the same way as we do for integers. We'll write this g vertical bar f, pronounce it g divides f. If there's some polynomial in the polynomial ring with the same kind of coefficients, so that f is equal to a times g. All right, I'm not going to say the of x's here. I tried to be good and write them because the author is, but I'm going to pronounce equations like this as f is equal to a times g. I'm not going to say f of x is equal to a of x times g of x, because I'll go insane by the end of this video. So f is equal to a times g. That's what it means for f to divide g. F is a polynomial multiple of g is another way we can use that. You can use the same kind of language. So g divides f, f is a multiple of g, they mean the same thing. Here's a couple of observations, and as we approach the end of our course, I'm going to keep pointing out that anytime I suggest an exercise or an observation, that's a euphemism for a possible final exam question. So a couple of observations that I'm just going to say and let you think about the details. You can maybe ask me about them in an office hour or something like that. If both f and g are non-zero, yeah, because g in the definition, the thing you're dividing by, can't be 0. But if f isn't 0 either, then if g divides f, it follows that the degree of g is no more than the degree of f. All right, so that's kind of one observation. Another observation is that g divides f if and only if the ideal generated by f is contained in the ideal generated by g. So I could have just given that definition. I could have said one polynomial divides another if those ideals are contained, because it's an equivalence. Good, so those are nice exercises for you. Let's continue here. Got a second definition, another flashcard for you, the greatest common divisor. So you give me 2 polynomials, they both can't be 0. One of them can be, but they both can't be 0. Then I'm going to call a polynomial d of x the greatest common divisor of f and g. Well, first of all, if it's monic, it has a leading term equal to 1. And then, well, I want it to do what the greatest common divisor should do. It should divide f and divide g. It's a common divisor. And since polynomials don't have size, the greatest part I'm going to replace with this, that if h is any other polynomial that divides f and g, h has to divide d. Okay, so that's what I mean by the greatest common divisor. By this definition, as Herstein says, we don't even know that the greatest common divisor of two polynomials even exists, but this is how I'm defining it, okay? So it's a monic polynomial that divides both f and g. Any other polynomial that divides both f and g is divisible or divides this d. Excuse me, it divides this d. It's the greatest common divisor. So I have a theorem that says, yeah, the greatest common divisor exists. The theorem says this, that if you take f and g, then this set I that consists of all polynomial linear combinations of f and g. So I take a polynomial a, I take a polynomial b, I multiply them by f and g, add them together, let a and b range over all polynomials, that sets an ideal in the polynomial ring. Okay, and if without loss of generality, say g is not 0, then the monic polynomial that generates that ideal, we proved last time there's a unique monic polynomial that generates that ideal, that thing's the greatest common divisor of f and g. All right, so this is how I'll prove it exists, because it's the unique monic generator of the ideal defined in the statement of the theorem. Okay, so you can take a look. Herstein writes the proof on page 158. I personally think it's a good exercise. You guys need to practice showing sets that are defined like this, defined with some condition, or subgroups and ideals. So I'm going to leave it as an exercise to you that set is an ideal. I'm going to leave it to you. It's written out in your book on page 158, but if I were you, I would try to prove that on my own before I went and read Herstein's proof. But for purposes of this video, keeping short, I'm just going to say, okay, that's your exercise. That sets an ideal, given f and g, and they don't have to be. If f and g are both 0, then the set I is equal to 0, and that's an ideal as well. So for any f and g, that sets an ideal. All right, now a kind of an observation. If I take the polynomial multiplier, let me see if I can leave the definition. If I take a to be 1 and b to be 0, well, that shows that f belongs to that set. Yeah, because 1 times f plus 0 is f. Likewise, g is in there. Take a to be 0 and b to be 1. So that set I contains both f and g. Okay, no matter what f and g are. If g is not 0, then I is not the 0 ideal. And we proved in theorem 4.56 last time that if I is not a non-zero ideal in this ring, then it's generated by, well, if you make it monic, a unique monic polynomial of minimal degree. All right, so D is the unique monic polynomial in I. It has minimal degree, and it generates that thing. Okay. So now what have I got to do? I've got to show you that D is a greatest common divisor. I've got to show you it meets that definition. So I've got to show you that D divides F, that D divides G, and that anything else that divides both F and G divides D. That's my goal. All right, so let's see if we can't start setting out about doing that. So first of all, we've already said F belongs to I. So F is in the ideal generated by D. That means that F is D times something. I'm calling the something P of X. So F is some polynomial multiple of D, and that means that D divides F by definition. All right. Similarly, I'll let you walk through the details, but because G belongs to I, D also divides G. So there you go. D is a common divisor of F and G. So for the last part, suppose I have some polynomial H that also divides F and G. All right, got to use the definition of divides. If H, my screen froze. If H divides F, well, then by definition, F is H times something, calling it P of X. And likewise, if H divides G, then G is H times something. I'm calling this something Q of X. Okay, that's the definition of divides. Okay, well, my polynomial D belongs to I, it generates it, so D has this form for some A and B. D is equal to AF plus BG for some A and B because it belongs to I. Everything in I has that form, right? All right, so now let's just substitute all this stuff in. I've got D, it's AF plus BG, but we said that F was P times H and G was Q times H, so I'm just substituting those things in there. And then in that form, I can see both those terms have an h in them. This one has an h, that one has an h, so I factored the h out. All right, so what have I got? D is h times something. What is the something? Well, it's AP plus BQ, but I don't really care about that. That something's a polynomial. So by definition, h divides d, so d is the greatest common divisor. We said d was monic, so d is the greatest common divisor of f and g by definition. All right, good. So the greatest common divisor of two polynomials, I think the way you want to think about it is that it's the monic generator of the ideal generated by those polynomials. What do I mean by the ideal generated by those polynomials? I mean, sorry for the scrolling, where is it? I mean this thing. The ideal generated by those polynomials is that thing. Its unique monic generator is the greatest common divisor of f and g. Nice. Okay. Corollary of that, because D belongs to that ideal generated by it, if D is the GCD of f and g, then you can write it as a polynomial linear combination of f and g. That's an important fact. We've used that fact about integers all the time, that the greatest common divisor of two integers is an integer linear combination of the integers. Well, the greatest common divisor of two polynomials is a polynomial linear combination of those polynomials. Important fact. Okay, so moving along here, a new vocabulary word, third flashcard of the video. I'm going to call two polynomials relatively prime if their greatest common divisor is 1. Hopefully that definition goes down pretty smoothly, because that's exactly what we mean by relatively prime integers. Two integers are relatively prime if their greatest common divisor is 1. So I mean the exact same thing for polynomials. Two polynomials are relatively prime if their greatest common divisor is 1. Okay? Next result, theorem 459. I think that if you haven't already done it, stop the video, go back into chapter 1, compare this theorem to theorem 1.54 on page 25. It's exactly the same theorem, but we're stating it here for polynomials. Theorem 1.54 is about integers. But the theorem says that two polynomials are relatively prime if and only if you can find two polynomials f and g are relatively prime if and only if you can find polynomials a and b that the linear combination af plus bg is 1. Yeah, one part of this theorem is just it's just a special case of this corollary. Yeah, the corollary says the greatest common divisor is always a polynomial linear combination. Well, if f and g are relatively prime, their greatest common divisor is 1 by definition. So of course 1 is a polynomial linear combination of them. That's the first part of this proof. I'll show you the proof down here. But yeah, if you take two polynomials that are relatively prime, well, this 1 is a linear combination of them by that corollary. D of x is 1. It's the constant polynomial 1. Now, the converse is kind of equally done. I mean, it's if you take two polynomials f and g, and you can write 1 as a polynomial linear combination of them, well, then 1 would belong to that ideal generated by f and g. Yeah, I'm using the ideal I, the same notation as the theorem we proved above, 457. Well, if 1 is in that ideal is everything. It's the ideal generated by 1. Yeah, and we said that the monic generator of the ideal is the GCD, while the monic generator of the ideal generated by 1 is 1. So 1 is the GCD of f and g. Cool. Our last result of what will be, I hope, a short video, and we can talk about this stuff in class. It's a short video, but it's got a lot of mathematics in it. So I hope you're pausing this and kind of filling in as much detail as you need to in your notes. Our last result, it's sort of a polynomial ring version of Euclid's lemma. Euclid's lemma, I'll remind you, is stated as theorem 1.55 on page 25. So what does Euclid's lemma say? I'm going to state it here for polynomials. It says if you take two polynomials, I'm using the same notation as the author, is not being very consistent with letters, but what are you going to do? We bought the book. You take two polynomials q and f that are relatively prime, and then you suppose that q divides f times something else. Here I didn't write this very carefully, I guess, where g of x is also some polynomial in f of x. Yeah, so q and f are relatively prime. Q divides the product of f and g. The statement is then q has to divide g. Yeah. This is just like with integers. Q doesn't have anything to do with F, but it divides this product, so it has to divide G. And if you're looking at the proof of that theorem 1.55, I'm about to give it again. I'm just doing it for polynomials instead of integers. Because by our result above, 459, if Q and F are relatively prime, then I can write 1 as a linear combination of them. What are the A and B? I don't know. They're the polynomials that make this true. They're polynomials over F. That theorem 4.59 says they have to be out there. So then just multiply that equation both sides by G. You see what I did? I've got my A, Q, I multiply it by G. I've got my B, F, I multiply it by G, 1 times G. Certainly if I multiply both sides of an equation by G, it still holds. All right, but if Q divides F times G, well, then that means F times G is Q times something. I'm calling the something H. Right? This feels just like we're doing number theory in the integers. Ring of polynomials over a field behaves a lot like the integers. All right, so now we just got to put all this together. Let me just show you the algebra here. So I've got my G, and what have I got? I've got this. I'm just taking this expression, actually, and I rewrote it the other way. So G is equal to AQG plus HFG. But then I'm going to replace the FG with Q times X, because we said that F times G is Q times, or sorry, Q times H. FG is Q times H. It's written right there. All right. And now you can see in this sum, I've got a Q of X in both summons. It's in the middle, AQG over here, BQH is in the middle in both places, actually. So you can factor it out. So what have we shown? We've shown that G is a polynomial multiple of Q. Well, that exactly means that Q divides G. That's the proof of that theorem. All right, so I'm going to try to keep this video short. I'm trying to help you read this long section 4.5. So we today just discussed all the results that you'll see on page 157 to 159. And we have one more lecture to finish section 4.5. So I thought I'd tell you what we're going to do. We're going to wrap up that section next time by bringing in this notion of prime, an analog of prime. So just like integers, polynomials kind of have a notion of a prime polynomial. We won't call them prime, we'll call them irreducible, but they sort of play the same role. And just like in the integers, how every positive integer can be factored into a product of primes in kind of a unique way, we're going to see that every polynomial can be factored into a product of these irreducibles in the same way. Right, so we're going to talk about kind of the analog of the fundamental theorem of arithmetic for the polynomial ring over a field, but that's next time. So thanks for listening.